So we have the core practical two. What is the core practical two? Make up a volumetric solution and carry out a simple titration for acid-base titration. How we can then make a solution, like practically how it is done. This is a very important experimental procedure to make up a solution. So what we do, like for example, we weigh a small bottle which containing a required mass of a solid on a normally two decimal place balance. So we have this is called a volumetric flask. Same thing, a volumetric flask is also having only one label. Like example, if it is a 500 ml volumetric flask, so there will be only one label 500. It will not be written 500, only one mark was there. Usually in the lab, we use 250 ml volumetric flask. So there will be only one line which is representing its 250. So how we make a solution? So first what we do, we transfer. So weigh the sample bottle, like the sample bottle is actually containing a required mass of a solid. Then we transfer that into a beaker. So we transfer that solid into a beaker from the sample bottle. Then we reweigh the empty sample bottle and record the mass difference, because the mass difference, like let's say we have a sample bottle was there. Yes, basically acid and like usually alkalis are not aqueous. You know, alkalis in the lab which we use, like example, we are using a sodium hydroxide or using a potassium hydroxide. These are pellets. White pellets are there for these. So first what we have to do, we have to make a solution. So how to make a solution for these and a standard and solution. So how we can make, so we have a sample bottle, we measure the mass of the sample bottle with a sample, and then we remove the sample out, we'll got the mass of empty bottle. When we take a difference of the two masses, we'll know what mass of a sample is used here. So we take a beaker and we transfer the sample into a beaker. We measure the mass of the the sample bottle with a sample, and then we measure the mass of empty sample bottle, and we take a difference of the two, so we'll know what mass is added here. Now we transfer that into a beaker, then add 100 cm cube of a deionized or a distilled water into a beaker. So we add a water, 100 cm cube of a water is added. Look, if we have a volumetric flask 50 cm cube, we don't add, like if we have a 250 cm cube volumetric flask, we don't add 250 cm cube, we just add 100 cm cube, okay? So we add like less than what is the volumetric flask is needed. And use a glass rod to stir, that will help in dissolving. So we use a glass rod, we stir it so it can dissolve. But sometimes the substance may not dissolve well. So in a cold water, so what we can simply do, the content can be heated gently until all the solid has dissolved. So we can heat it gently so that it will dissolve. Then after dissolving a substance, we pour that. This is written 500, let's say, but we have 250 ml. So after that, we pour this into a volumetric flask. But when we pour this into a volumetric flask, it will not reach the mark, because we just use 100 cm cube of a deionized water. So it will be somewhat here, or because its total is 250, so it will be somewhat here. Cm cube and milliliters are the same idea. Sometimes, so then we pour a solution into a 250 cm cube graduated flask via funnel. So what we do, like this is a graduated flask or a volumetric flask, we remove this lid and we place a funnel here and we transfer that by using a funnel. Then we rinse the beaker and the funnel and add the washing from it. So once a solution is being transferred, the beaker will looks empty, but still some part is there. So we add a deionized water and or a distilled water, and then we transfer that again. So when we transfer the washing, maybe the volume will increase but not reaches the mark. Then what we do at the last, we will reach a level by adding a deionized water or distilled water. So we add a water, we'll add a water until it will reach the mark. Now what we do, we place a lid on this volumetric flask. So on the top of this volumetric flask, we place a lid and we shake this volumetric. But normally, how a volumetric, instead of shaking, what we just simply do, we flip this volumetric flask, invert the volumetric flask. One, twice, thrice, multiple times until we have a thorough mixture of this substance which we are using. So we make up the mark with the distilled water using a dropping pipette for a last few drops and invert the flask several times to ensure that the uniform solution is being formed. Is it clear how we make a the volumetric solution for using it titration for titration? So the graduated flask, or you can also say a volumetric flask, has only one mark on the neck, which with the level to fill, which get an accurate volume. Yeah, they can ask why we use a deionized water or a distilled water, because the distilled water contain does not contain impurities, the soluble impurities. The tap water contains soluble impurities as well. That's why we did not use the tap water, we use a distilled water. So distilled water does not contain soluble impurity. We can also use this method for diluting a solution. Look, what is the purpose of a diluting a solution? Example, if I have a very high concentration of acid or alkali and I'm using in a titration, so if this is a very high concentration is there even in an acid or an alkali, and if I'm using for a titration, let's say this is a high concentration acid, and I fill up the burette with an alkali and I add alkali from the burette. But because if the concentration is very high, I need a very large volume. And the problem is that the burette can maximum hold 50 cm cube. That is the maximum volume which the burette can hold. So what if for this high concentration of the acid, I instead of 50 cm cube, I need more than 50 cm cube. Let's say I need 70 cm cube. But 70 cm cube, the problem with the 70 cm cube is that we have to refill the burette, and when we have to refill the burette, that will be experimental difficulty because during the experiment you fill the burette once, then you have to refill it. In that case it won't be accurate. It increases the chance that you may not get an accurate result. So what we prefer, to avoid a refilling of the burette, what we have to do, we have to make the solution with a high concentration, we want to make it dilute. So how we make a dilute solution of this? So we don't do the titration with a high concentration solutions. So first we use a dilution factor. How we dilute them? So same technique is used. We use a volumetric flask. Like let's say we pipette out only 25 cm cube of the original solution. Like the solution which was here, it was 25 cm cube. So instead of directly using it for titration, I transferred that into a volumetric flask, the high concentration, highly concentrated solution, which is 25. Then we add a deionized distilled water in this. It's a volumetric flask, so we add a distilled water until it reaches the mark. Then we place a stopper. Then we place a stopper and we invert the flask several times so that it will have a uniform mixing. Once it is mixed thoroughly, we don't like now the solution is a dilute. So as the solution is a dilute solution and a uniform concentration, which is now 250 because a volumetric flask is 250 cm cube. Now we again take 25 cm cube and do titration with 25 cm cube. But this 25 cm cube of a solution will contain less moles, so it needs less volume of an alkali for a reaction. So we don't have to refill the burette. So normally, whenever a reaction involves a high concentrations of solutions, acid or an alkali, we first dilute them and then we take out the diluted solution and we carry out a titration from that diluted solution. But when I work out the moles, what will the original moles, how I work out? Let's say when I carry out the titration, I got 0 0.1 moles here or 0.05 moles here. So what will the original solution consist of? How many moles? Because this is 250 cm cube and here is 25 cm cube. So it means the original solution is 10 times the volume. So the original moles will also be 10 times. So the original moles which are present in the solution will be equals to 0.5. So in a calculate for experimental point of view, we just use a very small concentration. And again, this is we minimize the risk. How we minimize the risk? Because if we use a dilute solution, acids and alkalis are corrosive. So we use a dilute solution, so we minimize the risk that it will cause or it the risk is there when you're using a high concentration like it is like corrosive is hazard, but we may it has a risk that it will likely to cause harm. So as a result, what will happen, we lower the concentrations. Is it clear? Diluting a solution, any doubt in this? Next is a core experiment of making a volumetric solution and carrying out a simple titration. So a journal method is there. You can see these are the apparatus which we use in a titration. We have a burette. As you can see, this is a burette with a jet opening is there, a pipette, and we have a conical flask. This is a pipette filler. This is a pipette filler like and this is make sure the bottom of the meniscus is in line to the neck of the pipette like meniscus. If you we have the bottom and the top, we always read for the bottom of the meniscus, and in this case maybe the meniscus might be clear to you like the curvature. So the bottom of the meniscus should be in line, okay, because we use the bottom of the meniscus for these acids and alkalis. Aqueous solution bottom meniscus is used. If the meniscus is top, how would we measure? If it was a top meniscus, then how it should looks like. First, top of the meniscus is there, then it should look like this. Like that is how you should keep it. Like this is a marking on the pipette. Then if you want, if a solution you want to use the top of the meniscus, then the level should look like this. If you want to use the bottom of the meniscus, then the level should look like this. Okay. That's how it should be. So the core practical, make a volumetric solution and carry out a simple acid-base titration. So first what we did, we rinsed the equipment. Normally a burette with acid and a pipette with an alkali and a conical flask with a distilled water. Then pipette 25 cm cube of alkali into a conical flask. You can see here, this is a pipette filler is there attached. So we pipette out 25 cm cube and transfer that into a conical flask. Then add acid solution. Like example, a burette is filled with an acid, and add few drops of indicator as well. Make sure that the jet space in the burette is filled with an acid. How we can make sure that the jet space, like this part, because usually when you fill up the burette, you fill it from the top. So when you fill the burette from the top, so there is a air present. So there in a jet there might, like you will see a level like this. So the black line is representing a liquid, an acid, but the jet is not completely filled. So what you do, you just run down additional acid. When you run down additional acid, the air will also be removed till the jet here, till this jet will also have acid. Then we add few drops of indicator. What are the indicators we can use? Which indicator we can use here? Different indicators are there. Like example, referring to the color change, if you are using a phenolphthalein, what if there are gas bubbles does not increase? Yeah, if there are gas bubbles present initially, then the volume which you record, it will appear that its larger volume is used. Because if you have a burette and there's an air bubble, like you fill up the burette and there's an air bubble or air is trapped. So when you open the tap, the air is removed and then the acid is coming out. So the total volume which appear to be higher than actually what is used in the experiment. So we add few drops of indicator by using a dropper or a teat pipette. If a phenolphthalein is used, these are the common indicators we use. It will be pink in alkaline and it is colorless in acid. So in this example, the conical flask was filled with an alkali and from the burette, we were adding an acid. So what is the original color? If phenolphthalein was used, then the original color will be, because phenolphthalein is pink initially in alkaline solution. But when you are adding an acid first initially, when you add an acid, there won't, because the amount of alkali is still enough. That's why there is no color change. Acid will be used up. Once all of the alkali is being used up, now the solution will be slightly acidic. The moment solution is slightly acidic, that is means you reach the end point, and phenolphthalein in acidic medium, it is colorless in acidic. So what is a color change? That the pink color, original pink color will disappear. Originally it will be pink, but then it will change. But if you use a methyl orange is yellow in alkaline and it is red in acidic, but at the end point means in a neutral solution, it will be orange. Yeah, the idea is that the when acid completely neutralize an alkali, phenolphthalein indicators show a color change. So usually, like because in case of a methyl orange, it changes from yellow to orange, and then if more acid is there, it will turn red. But a very small proportion, it will be orange in color. and we use a white tile underneath the flask to observe the color change. And when acid is mixed with an alkali, we should always swell the mixture and add acid drop wise at the end point. But usually, whenever we are doing this experiment, the first part is all the first ways method is called, like the first titration is called a range finder. What is a range finder? In a range finder, what we do? We take a conical flask, we fill it with an alkali, like example 25 cm cube of alkali is there, and we just open the jet of this burette. When we open the jet of the burette and just swelling, we just open it so that the moment it show a color change, we'll stop. So the moment when it show a color change, we'll stop. That is a range finder because the jet was open for a long time. So let's say we remove 28 cm cube. So if you use 28 cm cube of acid from the burette, so what this gives an indication that the volume required will always be less than 28 cm cube. Like, because what we did, the first experiment is always a range finder. It's a rough titer. What we do in a rough titer, we take a conical flask which is filled with an alkali and an indicator is there. We just open the jet and just swell the mixture. So you will have a rough idea that at around what volume there will be a color change. So that what is the use of this doing it? So let's say I worked out this range finder and I got 25 cm cube as my range, like around 25. So around 25, I'll get the range, like around 28. I know that the range is 28 or less. So when I reach, so first 20 cm cube or like, let's say when I add, because rangefinder is 28. So when I added like 22 or 23 cm cube, I'll add them quickly. But when I move from 23 to 28, I will add drop by drop, like very small quantity. Otherwise, if from the beginning you start adding drop by drop, what will the problem? It will take a very long time. Because if I say the color change should happen or occur around 28 cm cube, let's say, or 27.1 cm cube. So if you're adding from the beginning of the experiment, if you're adding drop by drop, what will happen? It will increase the uncertainty. Like it will take, like, not about uncertainty, it's about the time. It will take a very long time to do the first experiment itself. So always, whenever experiment is done in titration, we always do a range finder or a rough titer. And then how you know that how many times you should do the experiment until at least two results are concordant, like they're within the range of zero point 0.1 or zero point 0.2 is also acceptable. Like when I did the first experiment, the range finder, I got 28, let's say. When I do the second experiment, I got 26.9. When I did another experiment, I got 26.4. When I did another experiment, so should I repeat? Yes, I should repeat because the this is a rough titer. This is like a rangefinder is there. This is a first titer. This is a second titer. Because the difference between them, it should be plus minus 0.2. 0.2 is acceptable, a concordant. No, no, rangefinder depends on the different experiment. Like I'm giving just an example. Let's say for this experiment, you have a rangefinder 28. Like 28 cm cube of the volume you remove from the container the first time. And you observe a color change. So you will have an idea that when you reach around this value, like 28 or 25 or 26, you should add drop by drop. So you should, because the value difference is more than 0.2, so you should repeat for third one. So let's say we got 26.3. So now the two, and it's not like the second and third should be same. Let's say I have a value 26.8. So now first and third are same, so then I'll stop it. So even if first and second are same, I'll stop. Like same means concordant results are there, at least two concordant results within a range of 0.1. 0.1 is the best thing you do, but 0.2 practically is acceptable. Is it clear? this procedure? Anyone having a doubt or a question in this? What is the range of anomalous if a value is point plus minus point 0.2 more or less? You will consider that. Otherwise, you will ignore that. So, example, if one value is, let's say, 25.1, another value is 25.3. Should I repeat or should I stop? Should I do another titer or should I stop? No, we should stop. Why we should stop? Because the two values are in the range of zero point 0.2. Like they are zero point 0.2 more or less. The difference between them is zero point 0.2. So we stop it. But let's say another student performed the titration. Um, I'm not listing a range finder here. He got first value as 26.1. He got second value as 26.9. So should he do another titration? Yes or no? So you do another titration because the difference is large. When he did another, he got 26.3. Should he repeat, like should he do another titration or stop? So you can compare the first and the third result. So when you take a mean of these titer, so normally a mean is substituted, so 26.2 will be the mean. If the three are there, so it's just a range finder. The first one is a range finder, and then we take the mean of that. So normally, like what is a standard phrase? One substance that is generally one we don't know the concentration, we put in a conical flask. And it is measured by using a volumetric pipette, and the other substance is placed in a burette. So when we say titrate solution A with solution B, which means the A should be in a conical flask and B should be in the burette. And this is the same thing, like example, when we are carrying out a titration using a pipette, so we rinse the pipette with the substance which we want to fill up. Normally, if we want to fill up in with an alkali, so we rinse with an alkali. You can see this is a burette. So burette should be rinsed. Why rinse? Because maybe other reagents are there. Other reagents are there to remove that or to remove the inaccuracy. That's why it is rinsed. Whenever experiment, because in experiments we use the substances many times, we use these apparatus many times. That's why we always rinse them. So the burette should be rinsed with the substance that will be put in. If it is not rinsed out, acid or alkali added, maybe diluted the residual water in a burette. And this, so normally first what we do, we rinse with the distilled water, and then we would rinse with the substance which we want to fill. Like if I want to fill the pipette, I want to fill the pipette with an alkali. So first what I do, I rinse it with the water to remove any impurity from the previous experiments. And then I will rinse with an alkali. If I want to fill the burette with an acid, so first I'll rinse it with water, the distilled water, and then I will rinse with a acid, which we want to fill up. And do not leave the funnel in the burette because some drops of a liquid may fall. Like usually we use a funnel to fill up this burettes. So we fill up by using a funnel. So we don't leave this funnel. because some of the liquid might be there in the funnel and it will add it up into a burette, and that will cause inaccuracy in the results, the final results, the volume which we remove. And we make sure that the jet space in a burette is filled, as you can see here, with the solution, and air bubble is completely removed. If the jet space in the burette is not filled properly before we starting the titration, it will lead to an error, because if it then fill during a titration leads to a large than expected titer. So we should always, and how we can discard, we just open the tap here. So we remove all of the liquid, all of the air out from this jet. Then whenever you are reading, we always read for the bottom of the meniscus. Like example here, the burette readings are there. So reading the bottom meniscus of the burette, as this readings looks like, this value is there. About the volumetric solution, do we know that the alkali or acid for known concentration? For the like example, if we have a analog meters are there, analog. If we have a analog scales, like example, markings are there. So let's say you have the marking, like the marking is there between two marks. One is 9.1, another is 9.2. In analog apparatus, remember what is the uncertainty? Uncertainty means the smallest value which we can record. So uncertainty is the half of the least count divided by 2. Because you can estimate the position, like if one mark is 9.1, another mark is 9.2, but the level is between 9.1 and 9.2. So you can estimate this level, you can say the level is 9.15. So what is the least uncertainty in the measurement when we are using a burette? Because smallest marking is 0.1 cm cube, okay? Like the smallest marking, the first mark, you will have, like, zero mark is there, the next mark is 0.1, the smallest. The least count is 0.1, but you can have the uncertainty in the measurement. You can also read 0.05 cm cube. How you can read 0.05 cm cube? Because the distance between the two markings is zero point 0.1, but if the level is between the two, you can estimate that it is 0.05. So if the level is between 9.1 and 9.2, so I can say it is 9.15 cm cube. So remember the uncertainty, there's a difference between a least count and uncertainty. Least count is the smallest marking on the instrument, okay? But the uncertainty is the smallest value which can be recorded. So the least count is of a burette is zero point 0.1, but the uncertainty is 0.05. Then when we are adding an indicator, usually indicators are weak acids. So we don't add too much. We add usually a small quantity of these indicators. Like example, you are adding a phenolphthalein. Initially, it's colorless. Like in alkaline solution, it is pink or purple. And when you are adding, But if you are using a methyl orange is yellow is there. At the end point, it will be orange and it will be in, you can say red or pink in acidic solution. That and the you can see the background, the base, we use a white tile. What is the reason of using these white tiles? So that we can observe the color change more prominently. Okay. So when you are adding a solution from the burette, we always swell the mixture and we add drop wise at the end point. Distilled water can be added into a conical flask during a titration to wash the sides of the flask after every titer, and it does not affect the titration because when we add, because the conical flask, it is the moles which are reacting. The moles which are reacting are depending on the number of the moles of a substance rather than a concentration. So when a conical flask is rinsed with the water, even some water is added to this, but it won't make any difference to the number of the moles. That's why when we rinse the conical flask with the distilled water, then we don't have to rinse with any other substance. But for acid and alkali, like a burette and a pipette, if we rinse with the water and then we have to rinse it with either an acid or an alkali again. So recording these results, taking a mean titer, as you can see, initial burette reading, final burette reading, taking a difference. And these are the titer which we use. So if we have like the first value is 24, the next is 24.5. So even we can stop here. We don't have to repeat in that. But if like because the difference like 24 and 24.5, so the difference is plus minus zero point 0.5. So the difference is plus minus zero point 0.5, yes, I have to do. But if the difference was within the range, so yeah, I have to repeat. So that's why in this case I have to do it again. When we do it again, 24.5 and 24.4, so the difference is zero point 0.1 between them. So we don't have to do another. So we'll use a second and the third value and take an average title. The safety precautions, acids and alkalis are corrosive, so we use at low concentration acids are, and we wear eye protection and the gloves. Is it clear about the acids? The uncertainty in measurements as well when you are carrying out a titration. No, we just check the results. If it is If this is 24, this is 24.4. So they have a difference of 0.4. This is zero point 0.1 difference. So we don't have to like second and third. If I have first and third same, then I'll compare first with third, like a zero point 0.2 difference. So any value could be compared. It's not like the successive title. You can also compare first with third. More we'll do about this experimental techniques. Today we'll have